in the boundless darkness between the stars, where light itself takes days to cross empty voids, and the sun is nothing more than a faint, distant spark, a lone Voyager continues its silent odyssey, one that began long before most of us were born. What if I told you that right now, as these words reach your ears, a small, fragile machine crafted by human hands is hurtling through true interstellar space at more than 38,000 miles per hour, carrying secrets from our entire species across distances so vast they defy everyday imagination? And what if I revealed that this same machine is on the verge of a historic milestone no human creation has ever achieved, before a moment when its signals will take a full day, an entire 24 hours, just to whisper back to Earth? The answer to that cosmic riddle lies waiting at the very end of our journey tonight, a revelation that will forever change how you see our place among the stars. So stay with me, keep listening through every chapter, every whisper from the void, until the final moments when the mystery unfolds completely. Welcome to Sleep Time Narratives, where we gently unravel the grandest stories of science, wonder, and human curiosity through calm, immersive storytelling that lets your mind drift alongside the cosmos itself. Consider for a moment the sheer scale of what we are about to explore together. Voyager 1, humanity's most distant ambassador, is no longer merely a probe exploring our solar system. It has crossed an invisible boundary into the great unknown, traveling more than 16 billion miles from the only home we have ever known. To put that distance into perspective, imagine stacking every mile you have ever driven in your lifetime. Every road trip, every commute, every vacation journey, and then multiplying it by thousands upon thousands. Even light, the fastest thing in the universe, takes more than 22 hours to travel from Voyager 1 back to Earth right now. That means when the spacecraft sends its faint radio signals, they race across the emptiness for nearly a full day before our giant antennas on Earth can catch them. And in November 2026, just months from today, that one-way journey will stretch to a complete 24 hours. One full light day. A distance so immense that if you could drive at highway speeds without stopping, it would take you more than 50,000 years to cover the same ground. Yet Voyager 1 does it effortlessly, year after year, decade after decade, still faithfully transmitting data about a realm we can barely comprehend. This is not science fiction. This is the quiet, ongoing reality of a machine launched in 1977 that has outlived its designers, outlasted its original mission, and now drifts alone in interstellar space as the farthest human-made object ever to leave our solar system. Nearly 49 years ago, it began its life as part of a daring twin mission, Voyager 1 and its sibling Voyager 2, built by teams of brilliant engineers who dared to dream that their creation might survive not just years, but generations. Today, it serves as our eyes and ears in a region where the sun's influence finally fades, where the solar wind gives way to the gentle breath of the galaxy itself. Its instruments, some older than many of us, continue to measure cosmic rays, plasma waves, and magnetic fields with a resilience that borders on the miraculous. Every signal it sends back is a triumph of human ingenuity over the relentless cold, radiation, and isolation of deep space. But why does any of this matter to us here on Earth? Because Voyager 1 is more than metal and circuits, it is a time capsule of our curiosity, a testament to what happens when humanity reaches beyond the familiar and into the infinite. In its long, silent journey, it has already rewritten textbooks, revealed worlds we never imagined, and now, in the interstellar void, it is teaching us about the very fabric of the space between stars. The interstellar medium, that thin soup of particles, dust, and magnetic fields that fills the galaxy, is no longer just theory. Voyager 1 is sampling it in real time, sending back readings that scientists on Earth analyze with a mixture of awe and urgency. These whispers from the abyss are faint, yes, but they carry profound truths about how our sun's protective bubble interacts with the wider cosmos, about the high-energy particles that rain down from distant supernovae, and about the invisible forces shaping the galaxy we call home. Imagine the spacecraft itself for a moment. Roughly the size of a small car, Voyager 1 spins slowly on its axis to keep its antenna pointed toward Earth, its power dwindling year by year from the decaying heat of plutonium fuel. Yet its radio transmitter, a mere 23 watts when it left Earth, still reaches us across billions of miles. That signal arrives so weak that it is less powerful than the energy used by a single snowflake landing on the ground. And still, our deep space network listens. Huge dishes in California, Spain, and Australia turn their ears to the sky, catching those precious photons and decoding the data before it is lost forever. Each successful transmission is a small victory against the entropy of the universe, a reminder that even the smallest voice can echo across eternity if we choose to listen. As we begin this journey together, picture the emptiness around Voyager 1. There are no planets here, no moons, no comforting blue glow of Earth on the horizon. The nearest star is more than 4 light-years away, a distance so great that even at Voyager's speed it will take tens of thousands of years to approach. The Sun appears only as the brightest star in a sky filled with millions of others, its light diluted to a faint point. Yet Voyager keeps going, its trajectory carrying it toward the constellation Ophiuchus, a direction chosen decades ago by the precise mathematics of gravity assists. Every second, it travels more than 10 miles farther into the unknown. Every hour, it adds another 38,000 miles to its record. And every day, it reminds us that exploration does not stop when the cameras are turned off or the funding runs low. It continues in the dark, in the silence, with quiet determination. This silent journey also carries something far more precious than data. It carries us, our hopes, our questions, our collective imagination. Scientists, engineers, artists, and dreamers from 1977 poured their best ideas into this machine, knowing they might never see its full story unfold. Today, we inherit that story. We get to watch as it approaches the one light day mark, a threshold that will mark the moment when communication becomes a daily conversation with yesterday. What will the data show us about the interstellar wind? How will the magnetic fields behave? Will we detect new particles or unexpected patterns that challenge everything we think we know about the space between stars? These are the questions that keep mission teams awake at night and that we will explore together, step by step, across every chapter of this documentary. The beauty of Voyager 1 lies not only in its distance, but in its solitude. No other human-made object has ever ventured this far. It is utterly alone, yet it is not forgotten. Thousands of people on Earth still monitor its health, adjust its commands, and celebrate every successful signal. In an age when our attention is pulled in 1,000 directions, Voyager reminds us of the power of long-term thinking, of building something that outlives us, of reaching for the stars even when the payoff is measured in decades or centuries. Its story is one of endurance, of human creativity refusing to be bound by the limits of our tiny planet. And as we drift alongside it in these coming hours, you will discover how its journey mirrors something deep within all of us: the quiet, persistent urge to know what lies beyond the horizon. We stand at the threshold of understanding a new chapter in cosmic history. Voyager 1 is not just drifting, it is pioneering. It is teaching us that the universe is far stranger, far richer, and far more connected than we once believed. The faint signals it sends are like messages in a bottle cast into an ocean of stars, and we are the fortunate ones on the distant shore still able to read them. So settle in, let your mind wander through the vastness, and prepare to be astonished by the resilience of a small machine that refuses to stop speaking to us from the edge of everything we know. The interstellar drift has begun. And its story, the full story, with every revelation about its past triumphs, its present whispers, and its future among the stars, awaits us in the chapters ahead. Stay until the very end, because the answer to that opening question, the milestone that will redefine how we think about distance, time, and humanity's reach, will finally be revealed when we arrive at the conclusion of this silent journey together. The void is calling. Let us answer it, one whisper at a time. To understand how Voyager 1 became humanity's farthest-flung emissary, whispering across the interstellar void after nearly half a century, we must journey back to a time when the moon landings were still fresh in the world's memory, and NASA was searching for its next great leap into the unknown. The year was 1977, a moment of remarkable cosmic coincidence and audacious human ambition. On September 5 of that year, at precisely 12 hours, 56 minutes and 1 second UTC, a thunderous roar shattered the humid Florida dawn at Launch Complex 41 on Cape Canaveral. A Titan III-IE Centaur rocket, standing 160 feet tall and carrying 1.4 million pounds of thrust, lifted off with Voyager 1 nestled in its nose cone. Flames licked the sky as the vehicle climbed, shedding its solid rocket boosters in perfect sequence until the Centaur upper stage fired and propelled the spacecraft toward the outer planets. This was no ordinary launch. It marked the beginning of one of the most extraordinary engineering triumphs in history, a machine designed not just to explore, but to endure the unimaginable harshness of deep space for decades beyond anyone's realistic expectations. The story of Voyager 1 truly begins years earlier in the minds of visionary scientists who recognized a once-in-a-lifetime opportunity. In the mid-1960s, aerospace engineer Gary Flandreau at NASA's Jet Propulsion Laboratory made a stunning mathematical discovery while studying orbital mechanics. The outer planets, Jupiter, Saturn, Uranus, and Neptune, were aligning in a rare configuration that occurs only once every 175 to 176 years. This planetary lineup created a natural grand tour pathway, where gravity assist maneuvers or slingshot effects could fling a spacecraft from one world to the next with minimal fuel. Instead of requiring enormous rockets for each separate mission, a single probe could ride the gravitational pull of each giant planet like a cosmic pinball, gaining speed and changing direction for the next leg of the journey. The alignment was so precise that the mission window was narrow, essentially a few weeks in the summer of 1977. Miss it. And humanity would have to wait another lifetime for the same opportunity. NASA seized the moment, but not without compromise. The original Grand Tour concept had called for multiple sophisticated probes visiting all 4 outer planets plus Pluto. Budget realities in the post-Apollo era forced a more pragmatic approach. What emerged was the Voyager program. 2 identical spacecraft, Voyager 1 and its slightly earlier launch twin, Voyager 2. Voyager 2 lifted off on the 20th of August 1977, taking the longer, more ambitious route that could eventually reach Uranus and Neptune. Voyager 1, launched 2 weeks later on that September morning, followed a faster, shorter trajectory, optimized to reach Jupiter and Saturn first, then swing outward into interstellar space. The twin design was brilliant in its simplicity and redundancy. Each probe weighed about 1,600 pounds at launch, roughly the size of a small car, yet packed with 10 scientific instruments, a high-gain antenna the size of a large umbrella, and 3 onboard computers that, by today's standards, possessed less processing power than a basic smartphone. Yet those computers were hardened against radiation, built with triple redundancy so that if one failed, the others could take over seamlessly. The true engineering marvel lay in the power system. Far beyond the orbit of Mars, solar panels become useless. Sunlight is simply too weak. So engineers turn to radioisotope thermoelectric generators, or RTGs, essentially nuclear batteries fueled by plutonium-238. At launch, each Voyager produced around 470 watts of electricity, enough to power a few light bulbs. The plutonium decays slowly, releasing heat that thermocouples convert directly into electricity with no moving parts. This system was engineered for longevity, and it has performed beyond all expectations. Even now, nearly 49 years later, the RTGs continue to supply just enough power to keep essential systems alive, though the output has dropped by more than half. Every watt is precious, carefully rationed by mission controllers who treat the spacecraft like an elderly relative whose every need must be anticipated. Imagine the scene at the Jet Propulsion Laboratory in Pasadena during those frantic months before launch. Teams of engineers worked around the clock, testing every subsystem under simulated deep space conditions, extreme cold, vacuum, radiation bombardment. The spacecraft carried redundant tape recorders, backup transmitters, and duplicate thrusters. Its cameras were state-of-the-art Vidicon tubes capable of capturing images in multiple wavelengths. Plasma detectors, cosmic ray sensors, magnetometers, and a plasma wave instrument would measure particles and fields no human had ever sampled. And tucked aboard both probes was something profoundly human, the Golden Record, a gold-plated phonograph record containing sounds of Earth, music from Bach to Chuck Berry, greetings in 55 languages, and 115 images of our world. It was Carl Sagan and his team's poetic message in a bottle, cast into the cosmic ocean with the hope that someday, somewhere, another civilization might find it. The launch itself was a masterpiece of precision. As Voyager 1 cleared the atmosphere, its trajectory was so finely calculated that it would reach Jupiter in just over 18 months, using the planet's gravity to slingshot toward Saturn at even greater speed. The entire mission profile was a ballet of orbital mechanics, where each planetary encounter was choreographed years in advance. No one knew for certain whether the spacecraft would survive the intense radiation belts around Jupiter or the punishing cold beyond Saturn. Yet the design philosophy was clear. Build it tough, build it smart, and give it every chance to keep going long after the original scientists had retired. Redundant systems meant that even if half the instruments failed, the other half could continue the work. Heaters protected critical components from freezing. The high-gain antenna was designed to point back toward Earth with exquisite accuracy. Even as the spacecraft tumbled through the void at 38,000 miles per hour, what makes this origin story so compelling is the quiet confidence of the people behind it. In an era when many viewed space exploration as a fleeting triumph of the 1960s, a small but dedicated group at JPL bet everything on a machine that could outlive them all. They understood that Voyager was not just about visiting planets. It was about pushing the boundaries of what human technology could achieve in the face of cosmic indifference. The probes were built to operate in temperatures near absolute zero, withstand micrometeoroid impacts, and function with power levels that would eventually drop to the equivalent of a few dim night lights. Their computers used magnetic core memory and assembly language code that had to be flawless because there was no easy way to fix bugs once the spacecraft was millions of miles away. From that September morning in 1977, Voyager 1's journey became a testament to long-term thinking in an age that often prized immediacy. The rare planetary alignment gave it the initial push, but human ingenuity gave it the staying power. Every subsystem was over-engineered with margins for the unknown. The radioisotope generators were expected to last at least 30 years. They have already exceeded that by more than 50%. The attitude control system, with its tiny hydrazine thrusters, has fired millions of times to keep the antenna aimed at Earth. Even the tape recorders, primitive by modern standards, were built with backups upon backups. As we reflect on this birth of legend, it becomes clear why Voyager 1 continues to inspire. It was never meant to be a short-lived visitor to the planets. It was designed from the very first blueprint as an interstellar pioneer, a machine that could drift for generations, carrying humanity's curiosity into realms we could scarcely imagine. The launch was the spark, but the true fire was the vision that a small group of engineers working with 1970s technology could create something capable of speaking to us across the gulf of decades and billions of miles. That same fire burns today in the faint signals still arriving from the interstellar medium, proving that bold dreams, when paired with meticulous engineering, can outlast the lifetimes of their creators. The silent journey that began with fire and thunder on a Florida morning has now carried Voyager 1 into the quiet dark between the stars. From those first moments of powered flight, every mile, every scientific discovery, every carefully preserved watt of electricity has led us to this present moment of wonder. The spacecraft that rose from Cape Canaveral in 1977 is the same one that now sails beyond the sun's protective bubble, teaching us about the galaxy's hidden currents and magnetic whispers. Its story is our story, a tale of ingenuity meeting the infinite, of a small metal craft refusing to be silenced by the vastness of space. And as we continue forward, every chapter will reveal how that 1977 launch set in motion a legacy that still unfolds, one faint radio pulse at a time, across the cosmic ocean. In the intricate ballet of celestial mechanics, where planets dance in their ancient orbits and gravity becomes the ultimate architect of speed and direction, the true genius of Voyager 1 reveals itself not in its launch, but in the elegant design of its path through the outer solar system. After the thunder of liftoff from Cape Canaveral in 1977, the spacecraft did not simply fly straight outward like an arrow shot into the night. Instead, it followed a meticulously choreographed trajectory that turned the giant planets themselves into natural accelerators, slingshotting it from one world to the next with a precision that still astonishes engineers today. This was the grand design, the mission blueprint that transformed two modest probes into explorers capable of crossing the solar system in a fraction of the time and energy that would otherwise have been required. At the heart of this design lay the gravity assist technique, a concept as old as the physics of orbital motion, yet executed with breathtaking sophistication in the Voyager program. Imagine standing on a moving train and tossing a ball forward to a friend on a faster train passing alongside you. The ball gains extra speed from the motion of your train without any additional effort on your part. In space, planets act as those moving trains. Their enormous gravitational pull bends a spacecraft's path, accelerating it and redirecting its velocity, while the planet itself loses an infinitesimally tiny amount of orbital energy. For Voyager 1, this was not theory, but the very mechanism that made its ambitious journey possible. The mission planners at NASA's Jet Propulsion Laboratory calculated that a direct flight to Saturn would have required a rocket so massive it was beyond the technology of the 1970s. Instead, they used Jupiter's gravity to provide a free boost of more than 35,000 miles per hour, then Saturn's gravity to fling the spacecraft outward at even greater speed toward interstellar space. The opportunity was extraordinarily rare. In the late 1970s, the outer planets aligned in a configuration that occurs only once every 176 years. Jupiter, Saturn, Uranus, and Neptune formed a natural chain of gravitational stepping stones. Voyager 1 was launched on a faster, more direct route, optimized to reach Jupiter in 18 months and Saturn in just over 3 years, after which it would use Saturn's gravity to bend its path sharply out of the ecliptic plane and into the interstellar void. Voyager 2, launched 2 weeks earlier, took the longer scenic route that would eventually visit Uranus and Neptune. The twin spacecraft were essentially identical twins with different destinies, each exploiting the same planetary lineup, but following slightly divergent paths calculated down to the second. The precision required was almost unimaginable. In 1977, computers were room-sized machines with less power than a modern pocket calculator. Yet the navigation team used them to solve differential equations that predicted the spacecraft's position to within a few kilometers after traveling hundreds of millions of miles. Mid-course corrections were planned years in advance, using tiny hydrazine thrusters that fired for fractions of a second to nudge the trajectory by mere fractions of a degree. One miscalculation of even 1/10 of a degree at Jupiter could have sent Voyager 1 missing Saturn by millions of miles. The engineers called it the pinball mission, where each planetary encounter had to be perfectly timed so the spacecraft would arrive at the right speed angle, and distance to set up the next gravity assist. Every parameter was modeled, simulated, and resimulated until the path was locked in with margins so tight they left almost no room for error. Voyager 1 carried a suite of instruments that turned it into a rolling scientific laboratory, each one chosen and engineered to survive the journey and return data no other mission could obtain. The imaging science system captured thousands of photographs using Vidicon cameras sensitive to visible and ultraviolet light, revealing details of cloud bands, ring structures, and volcanic surfaces never seen before. The infrared interferometer, spectrometer, and radiometer measured temperatures and chemical compositions of atmospheres and surfaces. Plasma detectors sampled the solar wind and charged particles, while the cosmic ray subsystem recorded high-energy particles streaming from distant supernovae. Magnetometers on long booms measured magnetic fields with exquisite sensitivity, and the plasma wave subsystem listened for the subtle oscillations of charged particles in space. A radio science experiment used the spacecraft's own signal to probe planetary atmospheres during occultations, and the ultraviolet spectrometer analyzed gases in the upper atmospheres. Every instrument was duplicated for redundancy, shielded against radiation, and designed to operate in the deep cold of the outer solar system, where temperatures plunged to -300 degrees Fahrenheit. The spacecraft itself was a masterpiece of minimalism and resilience. Its high-gain antenna, a 1-2-foot parabolic dish, had to remain pointed at Earth with sub-degree accuracy, even while the probe spun slowly for stability. 3 onboard computers, each with only 4,000 words of memory, handled everything from attitude control to data formatting. They used magnetic core memory that could withstand radiation levels far higher than modern electronics. The power came from 3 radioisotope thermoelectric generators containing plutonium-238, producing 470 watts at launch and slowly declining over time. Every watt was budgeted months in advance. Non-essential heaters were turned off, instruments were powered down during cruise phases, and data was stored on digital tape recorders before being beamed back in carefully scheduled bursts. What makes this grand design so captivating is the quiet elegance of its execution. There were no flashy engines firing continuously. There were no dramatic course corrections caught on live television. Instead, the mission unfolded with the silent precision of mathematics meeting the cosmos. The engineers back on Earth could only watch as Voyager 1 approached Jupiter, its speed increasing from the planet's gravitational embrace, then slingshotting onward toward Saturn with even greater velocity. Each encounter was a high-stakes gamble where the data return justified every risk. The path was so perfectly calculated that Voyager 1 reached Jupiter on the 5th of March 1979, exactly as planned, then Saturn on the 12th of November 1980, and from there was flung forever outward on a trajectory that would never bring it back. This blueprint was more than a flight plan. It was a declaration of human ingenuity. In an era when many doubted that spacecraft could survive beyond the asteroid belt, Voyager 1 proved that careful design, redundant systems, and profound understanding of orbital mechanics could carry a machine across the solar system and beyond. Its instruments were not merely passengers, they were active explorers, sampling environments no human eye had witnessed. The quiet precision of its path meant that every mile traveled was a triumph of foresight over chaos, of calculation over chance. As we follow Voyager 1 along this carefully engineered route, we begin to appreciate the deeper poetry of its journey. The gravity assists were not just clever tricks of physics. They were the universe itself lending a hand to humanity's ambition. The spacecraft became a partner with the planets, borrowing their momentum to reach speeds that would have required an impossibly large rocket otherwise. And as it left Saturn behind, its path carried it out of the plane of the planets into the vast emptiness where the sun's influence would eventually fade. The grand design had done its work. Now the real voyage into the unknown could begin. Every detail of this mission blueprint still resonates today. The same principles of gravity-assist navigation guide modern missions to the outer planets and beyond. The instruments, though primitive by current standards, return data so rich that scientists continue to analyze it decades later. The quiet precision that guided Voyager 1 across billions of miles with 1970s technology stands as a humbling reminder of what careful planning and relentless engineering can achieve. From the moment it left Earth, Voyager 1 was never merely drifting. It was following a path written in the language of the stars themselves, a path that would carry it from the fury of Jupiter's storms and the icy beauty of Saturn's rings into the silent edge of the solar system and, ultimately, into the interstellar realm where it still travels today. The grand design was the foundation. The planetary encounters that followed were its fulfillment, and the long, silent drift that continues even now is its enduring legacy. As we turn our attention to those first close encounters with the giant planets, remember that none of it would have been possible without the elegant, invisible architecture of gravity and foresight that set Voyager 1 on its historic course across the outer solar system. In the spring of 1979, humanity stood on the threshold of a revelation that would forever alter our understanding of what a planet could be. On March 5 of that year, after a journey of more than 18 months and 400 million miles, Voyager 1 made its closest approach to Jupiter, skimming just 172,000 miles above the giant planet's cloud tops. What the spacecraft's cameras and instruments revealed in those fleeting hours was nothing short of breathtaking. A world of unimaginable fury and beauty, a gas giant so vast that more than 1,300 Earths could fit inside it, yet alive with swirling storms the size of continents and volcanic activity so violent it reshaped an entire moon before our eyes. This was the moment when the outer solar system stopped being a distant, hazy concept in textbooks and became a vivid, living reality captured in color and motion for the very first time. Picture the scene as Voyager 1 drew near. Jupiter hung in the blackness like a colossal banded marble, its atmosphere a riot of creams, oranges, browns, and delicate blues. The spacecraft's narrow-angle camera, with its 1,500mm focal length, began snapping images that would soon flood mission control at the Jet Propulsion Laboratory. What scientists saw on their monitors left them speechless. The cloud bands, long suspected from Earth-based telescopes to be zones of rising and falling air, were revealed in exquisite detail as turbulent rivers of gas moving at speeds up to 300 miles per hour. White ovals and brown barges, smaller storm systems, drifted and merged like ships in a cosmic current, and at the center of it all loomed the great red spot, that iconic crimson oval larger than the entire planet Earth. Up close, it was no longer a simple red blotch. It was a towering anticyclone, a hurricane that had raged for at least 300 years, with winds circling at 250 miles per hour and clouds rising and falling in complex, layered patterns that resembled nothing so much as the eye of a living storm system. The sheer scale of the turbulence was mesmerizing. Lightning bolts, each one thousands of times more powerful than anything seen on Earth, flashed deep within the clouds, captured by Voyager's photopolarimeter as bright bursts against the night side of the planet. The radiation environment was so intense that the spacecraft's instruments registered levels high enough to damage electronics. Yet Voyager pressed on, its shielding and redundant systems holding firm. As the probe swung behind Jupiter, it used the planet's gravity to slingshot itself towards Saturn, gaining an enormous boost in velocity, while its cameras looked back to capture the planet in silhouette against the sunday. In those backlit images, scientists discovered something entirely unexpected. A faint, gossamer ring system encircling Jupiter, composed of tiny dust particles kicked up by impacts on the inner moons. A ring no one had ever seen from Earth suddenly materialized in the data, proving that even the king of the planets still held secrets. But the greatest surprise awaited at Jupiter's innermost large moon, Io. As Voyager 1 approached within 128,000 miles, its instruments began detecting something extraordinary. The moon's surface was not the dead, cratered wasteland astronomers had expected. Instead, it was a churning, sulfurous hellscape of yellows, oranges, and reds, dotted with black volcanic calderas and glowing lava lakes. On March 8th, just days after closest approach, the navigation team noticed an odd distortion in Io's silhouette against the stars. Analysis revealed a plume of material shooting 180 miles straight into space, an active volcano erupting with such force that it was ejecting sulfur dioxide gas and molten rock at supersonic speeds. This was the first time in history that active volcanism had been observed anywhere beyond Earth. Over the next few days, Voyager identified 9 erupting volcanoes on Io, some spewing fountains of lava higher than Mount Everest. The moon's surface was being resurfaced so rapidly that its entire crust could be renewed in just a few thousand years. Tidal forces from Jupiter and the other Galilean moons were stretching and squeezing Io like a rubber ball, generating enough internal heat to drive this planetary-scale furnace. The discovery sent shockwaves through the scientific community. Here was a world where geology operated on a timescale of days rather than millions of years. Io's volcanoes were not gentle Hawaiian-style flows. They were explosive, sulfur-rich blasts that painted the moon in vivid technicolor and fed a vast torus of charged particles that encircled Jupiter. This plasma torus glowed in ultraviolet light, creating a donut-shaped radiation belt so intense it posed a constant threat to the spacecraft. Voyager's plasma wave instrument picked up the eerie whistlers and chorus of charged particles dancing along Jupiter's magnetic field lines, sounds that, when converted to audio, resembled birdsong mixed with electronic static, an alien symphony playing across 400 million miles of space. The wonder extended beyond Io. Europa, the smooth, ice-covered moon, showed long, linear cracks that hinted at a subsurface ocean of liquid water beneath the frozen crust. Ganymede and Callisto revealed ancient cratered surfaces mixed with grooved terrain and possible ancient magnetic fields. 4 new small inner moons were discovered orbiting close to Jupiter's ring, each one a captured fragment of the planet's violent past. Every image, every data point expanded the catalog of what was possible in our solar system. Planets were no longer static orbs. They were dynamic, evolving worlds with weather systems, magnetic dynamos, and geological activity that challenged every preconception. For the engineers and scientists watching in real time, the flyby was both exhilarating and nerve-wracking. The radiation levels near Jupiter were so high that the spacecraft's computer experienced several temporary memory upsets, yet the redundant systems performed flawlessly. Commands sent from Earth took more than 30 minutes to reach the probe, meaning every maneuver had to be pre-programmed with perfect precision. When the first raw images began streaming back, the team gathered around monitors in Pasadena, cheering as each new frame revealed details sharper than the best Earth telescopes could ever achieve. For the first time, humanity was seeing Jupiter not as a distant point of light, but as a living, breathing giant whose storms and moons told stories of formation and evolution billions of years in the making. These revelations reshaped planetary science overnight. The Voyager Jupiter encounter proved that the outer solar system was not a frozen, dead region, but a laboratory of extreme physics and chemistry. The data returned filled entire rooms with magnetic tapes and sparked hundreds of scientific papers. School children across the world watched the images on television and dreamed of becoming astronomers. The sense of wonder was palpable. We had crossed an invisible line and entered a realm of fire, ice, and sulfur where the rules of our home planet no longer applied. Jupiter's fury was not destructive in a way that threatened Earth. It was creative, sculpting moons and rings and magnetic fields that continued to influence the entire solar system. As Voyager 1 receded from Jupiter, its cameras captured one final, unforgettable portrait. The planet in crescent phase, its night side illuminated only by faint auroras and the glow of volcanic plumes on Io. The spacecraft was now accelerating towards Saturn, carrying with it the knowledge that the solar system was far more diverse and dynamic than anyone had dared imagine. That single flyby in March 1979 transformed Voyager from a daring experiment into a legendary explorer, proving that a machine built in the 1970s could survive the harshest environment in the solar system and return treasures beyond price. The images and data it gathered still serve as the foundation for every mission to the outer planets that has followed, from Galileo to Juno and beyond. The encounter with Jupiter was the first planetary triumph of the Voyager mission, a moment when humanity's reach finally matched its curiosity. It showed us that even in the cold, distant reaches of our solar system, worlds could be alive with motion, color, and relentless energy. And as Voyager 1 continued its journey outward, those early images of swirling clouds, raging storms, and erupting volcanoes traveled with it in digital memory, a vivid reminder of the wonders that had already been uncovered and the greater mysteries that still lay ahead in the silent dark. In the quiet aftermath of its triumphant encounter with Jupiter, Voyager 1 turned its gaze outward once more, riding the invisible gravitational currents of the solar system toward its next destination, Saturn, the jewel of the outer planets. On the 12th of November 1980, after a journey of more than 3 years and over 700 million miles since leaving Earth, the spacecraft made its closest approach to the ringed world at just 124,000 kilometers above the cloud tops. What unfolded in those precious hours was nothing short of a revelation, a moment when humanity first beheld Saturn not as a distant, hazy telescope image, but as a living, breathing world of breathtaking complexity and poetic beauty. The data streaming back to Earth in real time transformed our understanding of gas giants forever, revealing ring systems more intricate than any artist could have imagined, new moons hidden in the shadows, and a mysterious companion world shrouded in organic haze that hinted at the very chemistry of life itself. As Voyager 1 drew near, its cameras captured images that still astonish today. Saturn's rings, long thought to be simple, uniform bands, unfolded into a dazzling architecture of thousands upon thousands of individual ringlets, braided strands, and sharp divisions. The spacecraft's high-resolution imaging system, working in tandem with its photopolarimeter, revealed that the rings are not solid but composed of countless particles of water, ice ranging in size from microscopic dust grains to boulders the size of houses. These particles orbit Saturn in a delicate gravitational ballet, shepherded by tiny moons whose gravity sculpts the edges of the rings into crisp boundaries. The famous Cassini division, visible even from Earth, proved to be far more than a simple gap. It was a region where orbital resonances with the moon Mimas had cleared a path, creating a dark lane 4,800 kilometers wide. Closer in, the ring showed Spoke's mysterious radial features that appeared and disappeared like ghostly clock hands, likely caused by electrostatic forces lifting tiny dust particles above the ring plane. Voyager 1 watched these spokes rotate with the planet, a dynamic phenomenon no one had predicted, revealing that Saturn's rings are not static jewelry but a constantly evolving system shaped by gravity, electromagnetism, and subtle collisions. The spacecraft's trajectory was a masterpiece of precision engineering. After the Jupiter gravity assist had accelerated it to over 35,000 miles per hour, Voyager 1 approached Saturn from below the ring plane, allowing its cameras to peer through the gaps and capture the rings in stunning backlit glory. As sunlight filtered through the billions of icy particles, the rings glowed like translucent veils, their shadows falling dramatically across the planet's golden atmosphere. The planet itself appeared as a vast, flattened sphere banded with subtle cloud features, its equatorial diameter stretching 120,000 kilometers, 9 times wider than Earth. Voyager measured Saturn's rapid rotation, a mere 10 hours and 39 minutes, which flattens the planet at the poles and drives powerful atmospheric winds reaching 1,100 miles per hour. These winds, far stronger than Jupiter's in some regions, painted the atmosphere in delicate pastel hues of ammonia ice crystals, creating a world that seemed both serene and tempestuous beneath its calm exterior. Perhaps the most poetic discovery came in the intricate dance of the ring's shepherd moons. Voyager 1 identified Prometheus and Pandora, two small potato-shaped satellites orbiting just inside and outside the narrow F-ring. Their gravitational tug-of-war keeps the F-ring's strands braided and confined, preventing the particles from spreading into a diffuse cloud. Even smaller moonlets were glimpsed embedded within the rings themselves, acting as miniature sculptors. These findings reshaped our entire model of how ring systems form and persist. Before Voyager, rings were thought to be ancient remnants of a shattered moon or primordial material. After Saturn, scientists understood that rings are dynamic, youthful structures constantly replenished by collisions and micrometeoroid impacts, with moons playing a crucial role in their longevity. The G-ring, a faint and previously unknown band lying between the main rings and the E-ring, was another surprise. Voyager's plasma wave instrument detected it as a region of microscopic dust particles likely ejected from the moon Enceladus, whose icy geysers would later be confirmed by subsequent missions. This faint ring, barely visible even in Voyager's sensitive detectors, hinted at hidden activity beneath the surface of Saturn's moons. No encounter with Saturn would be complete without its largest moon, Titan, and Voyager 1 provided our first close-up view of this enigmatic world. On November 12, the spacecraft passed just 4,000 kilometers above Titan's thick, orange atmosphere. What it revealed was a planet-sized moon larger than Mercury, wrapped in a nitrogen-rich haze so dense that its surface remained hidden from the cameras. Spectroscopic data showed a complex chemistry of hydrocarbons, including methane, ethane, and acetylene, creating an orange smog that absorbs ultraviolet light and scatters red wavelengths. Beneath that haze, Voyager detected hints of an atmosphere thicker than Earth's, with surface pressures 1.5 times greater and temperatures around -290 degrees Fahrenheit. The plasma and cosmic ray instruments measured how Titan's atmosphere interacts with Saturn's magnetosphere, creating a wake of charged particles that Voyager sailed through. These observations sparked decades of speculation about Titan's potential for prebiotic chemistry, the building blocks of life, and inspired future missions like Cassini-Huygens, which would later land a probe on its frozen surface and reveal lakes of liquid methane. In 1980, however, Titan remained a mysterious orange pearl, a world that seemed to hold secrets about how planets and life might evolve in the outer solar system. The scientific revelations from the Saturn flyby were profound and immediate. Voyager 1's magnetometer showed that Saturn possesses a powerful magnetic field, tilted slightly from its rotation axis and extending far into space, creating a magnetosphere that traps charged particles and produces auroras at the poles. The cosmic ray subsystem detected a drop in high-energy particles as the spacecraft entered the planet's magnetic bubble, confirming that Saturn, like Jupiter, shields itself from galactic radiation. Ultraviolet spectrometers measured the composition of the upper atmosphere, revealing hydrogen and helium as the dominant gases, with trace amounts of methane that give the planet its subtle coloration. Every instrument contributed to a new picture of gas giants as dynamic, evolving worlds rather than static orbs. The data forced astronomers to rethink planetary formation theories, suggesting that the rings and moons we see today are the result of ongoing gravitational sculpting rather than ancient leftovers. Yet beyond the raw science, the Saturn encounter carried an almost artistic wonder. The images returned to Earth in those November days showed rings backlit by the sun, appearing as delicate, glowing arcs against the blackness of space. With Saturn's shadow cutting a sharp wedge through the system like a cosmic sundial, the planet's subtle banding and the intricate ring divisions created compositions that rivaled the finest abstract art. Mission scientists, watching the data arrive in real time at the Jet Propulsion Laboratory, described the moment as humbling and exhilarating. For the first time, humanity had seen the rings edge on, revealing their paper-thin nature only tens of meters thick in places despite spanning hundreds of thousands of kilometers. This perspective transformed Saturn from a distant curiosity into a three-dimensional marvel, a world of ice, shadow, and hidden motion. As Voyager 1 completed its Saturn flyby and began the long, silent coast outward, it had already achieved far more than its designers had dared to hope. The spacecraft had not only survived the intense radiation of Jupiter, but had thrived at Saturn, returning more data in a few days than all previous observations of the planet combined. Its trajectory, carefully bent by Saturn's gravity, now pointed it toward the outer heliosphere and eventual interstellar space, carrying forward the momentum of discovery. The poetic beauty of those rings, the scientific upheaval they caused, and the tantalizing mystery of Titan all became part of Voyager's enduring legacy, proving that a small machine launched in 1977 could still rewrite textbooks nearly half a century later. The jewels of Saturn had been unveiled in all their intricate glory, their shadows and spokes dancing across the void, their shepherd moons guiding the choreography. In that single flyby, Voyager 1 had shown us that even the most familiar planets in our solar system held wonders we had never imagined. The gas giants were no longer distant points of light, but vibrant, active worlds with ring systems that told stories of gravity, collision, and renewal. As the spacecraft receded into the darkness, its instruments still recording the fading influence of the sun, it left behind a transformed understanding of our cosmic neighborhood, one where beauty and science intertwined in ways that continue to inspire every new generation of explorers. The silent journey had claimed its second planetary triumph, and the path ahead into the unknown had never seemed more promising. After the breathtaking encounters with Jupiter's raging storms and Saturn's glittering rings, Voyager 1 slipped quietly into the long, empty expanse beyond the last major planets. The year was 1980. The spacecraft had completed its primary mission with stunning success, yet its journey was only beginning. What followed was one of the most remarkable phases in space exploration history. A silent, decades-long drift through the outer solar system, a realm so vast and empty that it would take nearly a quarter century for the probe to reach the next invisible frontier. This was the era when Voyager 1 truly became a pioneer of the unknown, traveling farther from the sun than any human-made object had ever gone. Its instruments still alert, its radio voice still reaching Earth across billions of miles, even as the familiar worlds of our solar system faded into distant points of light. Imagine the spacecraft in those years. After Saturn, Voyager 1's trajectory carried it outward at more than 38,000 miles per hour, a speed it would maintain for decades. The sun grew smaller in its cameras until it was just another bright star among millions. The planets became faint specks, then disappeared entirely from view. There were no more gravity assists, no more close flybys, no more dramatic images of swirling clouds or icy rings. Instead, there was the long, steady cruise through the Kuiper Belt and beyond, a region once thought to be empty but now known to be filled with icy bodies and dust. Voyager 1's instruments, designed for planetary science, began a new chapter of discovery. Measuring the gradual thinning of the solar wind, the increasing intensity of galactic cosmic rays, and the subtle shifts in the magnetic field carried outward from the Sunday scientists on Earth watched with quiet anticipation. The heliosphere, the vast bubble of charged particles and magnetic fields, blown outward by the sun's constant wind, extends far beyond the planets. At its outer edge, this supersonic solar wind must slow dramatically as it presses against the thin gas and dust of the interstellar medium. That slowing happens at a boundary called the termination shock, a cosmic standing wave where the solar wind drops from supersonic to subsonic speeds, much like an airplane breaking the sound barrier in reverse. For years, models predicted this shock lay somewhere between 50 and 100 astronomical units from the Sunday. Voyager 1 was heading straight toward it, and every year brought it closer. By the early 2000s, the data began to hint that the boundary was near. Cosmic ray intensities climbed steadily as the sun's protective magnetic shield weakened. The solar wind itself showed signs of turbulence. Then, in late 2004, the instruments registered something unmistakable. On the 16th of December, 2004, at a distance of 94 astronomical units, more than 8.7 billion miles from the Sun, Voyager 1 crossed the termination shock. The event was dramatic yet subtle in the data stream. The magnetic field strength suddenly doubled, exactly as theory predicted when the solar wind compressed and slowed. Low-energy charged particles surged in intensity. The solar wind velocity dropped sharply, sometimes appearing to flow backward toward the sun in turbulent eddies. Plasma wave instruments detected a burst of noise like static on an old radio, signaling the collision between the sun's outflow and the incoming interstellar wind. Crossing into the heliosheath, the turbulent region between the termination shock and the heliopause, was like entering a cosmic shoreline where two great oceans meet. Inside the heliosphere, the solar wind dominates, a constant outward breeze of charged particles traveling at hundreds of miles per second. Beyond the shock, that wind slows to a crawl, becomes hotter and denser, and begins to mix with the galactic plasma pressing inward. The heliosheath is not calm. It is a zone of compression, magnetic reconnection, and energetic particle acceleration. Voyager 1's low-energy charged particle instrument recorded a steady rise in anomalous cosmic rays, particles thought to be accelerated at the shock itself. The magnetometer showed complex folded magnetic field lines, evidence of the sun's influence being squeezed and twisted by the interstellar medium. Yet the solar wind did not vanish. It simply changed character, becoming a slower, more chaotic flow that still carried the imprint of our star. This transition was no sudden leap. For years afterward, Voyager 1 remained inside the heliosheath, drifting through a region roughly the thickness of the distance from the Sun to the termination shock itself. The spacecraft's power levels were already declining, yet its instruments continued to function with remarkable resilience. The cosmic ray subsystem tracked high-energy particles from distant supernovae, particles that had traveled across the galaxy for millions of years before reaching Voyager. The plasma wave subsystem listened for oscillations in the surrounding plasma, providing indirect clues about density and temperature in this unexplored borderland. Each new data point was a revelation. Scientists had expected a relatively smooth deceleration. Instead, they found turbulence, magnetic bubbles, and regions where the solar wind appeared to stagnate or even reverse. The heliosheath was far more dynamic and unpredictable than models had suggested, a sign that our understanding of how stars interact with the galaxy was still incomplete. What makes this phase of the journey so compelling is the sheer loneliness of it. For more than 2 decades after Saturn, Voyager 1 traveled in near total isolation, its cameras largely turned off to conserve power. Its only connection to humanity, a faint radio signal that took more than 12 hours to reach Earth by the mid-2000s. Mission controllers at the Jet Propulsion Laboratory had to anticipate every command days in advance, knowing that by the time the signal arrived, the spacecraft would already be millions of miles farther out. Yet the probe kept working. Its redundant systems, built with 1970s technology, proved more durable than anyone dared hope. The radioisotope thermoelectric generators, though producing less electricity each year, still supplied enough power to keep the essential instruments alive. The attitude control thrusters fired precisely to keep the high-gain antenna pointed toward Earth, a feat of engineering that allowed data to continue flowing across distances that would have seemed impossible in 1977. In the heliosheath, Voyager 1 became humanity's first direct explorer of the Sun's outer frontier. The data it returned challenged long-held assumptions. Some predictions said the magnetic field would align differently. Instead, it remained largely in the same direction but grew stronger and more complex. Cosmic ray intensities rose, but not in the exact pattern expected. The boundary proved porous and dynamic, with the solar wind and interstellar medium intermingling in ways that suggested a more gradual transition than a sharp wall. These surprises fueled intense scientific debate and new models of the heliosphere, reminding us that even with sophisticated simulations, reality often holds revelations no computer can fully predict. As Voyager 1 pressed deeper into the heliosheath, the Sun's influence continued to weaken. The solar wind grew thinner, the magnetic field more tangled, and the flux of galactic cosmic rays more dominant. The spacecraft was now traveling through a realm where the Sun is just one star among billions, its protective bubble finally yielding to the wider galaxy. This long, quiet interval between the planets and interstellar space was not empty time. It was a period of profound scientific growth, a bridge between the familiar solar system and the truly unknown. Every faint signal from the instruments told a story of resilience, of a machine built in the 1970s, still teaching us about the cosmos in the 21st century. The heliosheath phase also carried a deeper philosophical weight. Voyager 1 was no longer visiting worlds we could photograph or name. It had entered a region defined not by visible landmarks, but by invisible forces, plasma flows, magnetic fields, and particle energies. In doing so, it expanded the very definition of exploration. We were no longer looking at planets through cameras. We were feeling the breath of the galaxy itself through the spacecraft's sensors. The data arriving on Earth was raw, often puzzling, yet it painted the first in-situ portrait of the edge of our stellar neighborhood. Scientists compared it to standing on a beach and listening to the waves before ever seeing the ocean beyond the horizon. This silent edge of the heliosphere set the stage for the next great leap. The heliosheath was the turbulent buffer zone, the place where the sun's domain finally surrendered to interstellar space. Voyager 1's instruments were already detecting the first hints of what lay beyond. A gradual increase in galactic particles, subtle shifts in plasma density, and the steady pressure of the interstellar wind. The long drift had prepared the spacecraft, tested its systems, and gathered irreplaceable data about a frontier no one had ever visited. And as the years passed, the probe continued its steady outward course, carrying humanity's curiosity into a realm where the sun's light and wind at last give way to the ancient currents of the Milky Way. The journey beyond the planets was never meant to be dramatic in the way the planetary flybys were. It was quieter, slower, more contemplative. Yet in its own way, it was equally profound. It showed that exploration does not always require fireworks or close-up images. Sometimes it is the patient accumulation of data across decades, the steady accumulation of distance, the quiet persistence of a machine that refuses to stop transmitting even as the void grows deeper. Voyager 1's time in the heliosheath was a master class in endurance, a reminder that the most important discoveries often happen not in the spotlight of a planetary encounter, but in the long, dark stretches between the stars. And as we follow its path further, those same instruments that first tasted the termination shock would soon carry us across the final boundary into interstellar space itself, where the sun's influence fades completely and the galaxy's voice becomes the only sound. The silent edge had been reached, the heliosheath had been explored, and the greatest leap of all still lay ahead. After the long, quiet years of drifting beyond the realm of the planets, something profound was about to happen, something no human-made object had ever experienced. Voyager 1 had already traveled billions of miles, surviving the radiation storms of Jupiter, the icy rings of Saturn, and the endless cold of the outer solar system. It had entered a region called the heliosheath, the turbulent boundary layer where the sun's protective bubble of solar wind begins to fray and weaken against the incoming pressure of the galaxy itself. For 8 long years, from 2004 to 2012, the spacecraft had been pushing through this chaotic frontier, its instruments recording a gradual but unmistakable shift in the environment around it. Then, on August 25, 2012, at a distance of more than 11 billion miles from Earth, Voyager 1 crossed an invisible wall that no one could see, no one could touch, yet everyone had been waiting for. The heliopause, the official boundary between our solar system and true interstellar space. This was the moment humanity stepped beyond the sun's domain for the first time. The heliopause is not a solid surface or a dramatic glowing barrier like the ones we see in science fiction. It is an invisible, ever-shifting membrane where the sun's outward-flowing plasma finally loses its battle against the incoming interstellar wind. Inside the heliosphere, the space around us is filled with particles blown outward from the sun at hundreds of miles per second. Beyond it lies the interstellar medium, a thin, cold soup of hydrogen and helium atoms, cosmic dust, and high-energy particles that have traveled across the galaxy for millions of years. Voyager 1 had spent decades approaching this threshold, and now it was about to pass through. The crossing itself happened without any fanfare on the spacecraft. There was no sudden jolt, no alarm, no dramatic change in speed. Voyager 1 simply continued its steady 38,000-mile-per-hour drift. But its instruments, some of them older than many of the scientists now monitoring them, began to register unmistakable changes. The flow of solar particles, which had been steadily decreasing for years, dropped dramatically almost overnight. At the same time, the intensity of galactic cosmic rays, high-energy particles originating from distant supernovae and other violent events across the Milky Way, suddenly surged. These particles had been partially blocked by the Sun's magnetic bubble. Now, with the bubble behind them, they poured in freely. The magnetometer on board recorded a shift in the direction and strength of the magnetic field, confirming that Voyager had moved from a region dominated by the Sun's magnetism into one shaped by the galaxy itself. For months afterward, mission scientists at the Jet Propulsion Laboratory pored over the data with intense excitement mixed with careful skepticism. The plasma instrument that would have given the clearest confirmation of the density change had stopped working years earlier, a victim of age and radiation. Without direct plasma measurements, the team had to rely on indirect evidence. Then, in the spring of 2013, a brilliant piece of detective work provided the final proof. In April 2013, a coronal mass ejection from the Sun, an enormous burst of solar plasma, finally reached the distant spacecraft, more than a year after it had left the Sun. When this wave of material slammed into the interstellar plasma surrounding Voyager 1, it caused the surrounding medium to oscillate like a ringing bell. Voyager's plasma wave instrument captured these oscillations, and from their frequency, scientists could calculate the exact density of the plasma. The numbers matched perfectly with what models had predicted for interstellar space. On September 12, 2013, NASA made the historic announcement. Voyager 1 had officially entered interstellar space on August 25th of the previous year. Humanity's first interstellar explorer had crossed the threshold. This achievement was nothing short of miraculous when you consider the age of the spacecraft. By 2012, Voyager 1 was already 35 years old, far beyond its original design life. Many of its systems had been turned off to conserve power. The cameras had been shut down long ago to save energy, yet the remaining instruments, radiation-hardened, triple-redundant, and engineered with extraordinary care, continued to function with remarkable precision. The fact that a machine built in the 1970s could still send back usable scientific data from beyond the heliopause is a testament to the foresight of the engineers who built it. Every watt of electricity from its decaying plutonium generators was carefully rationed. Commands from Earth took more than 17 hours to reach the spacecraft, and another 17 hours for the reply to return. Yet the dialogue continued. The data Voyager 1 began sending back from interstellar space was revolutionary. It showed that the interstellar magnetic field is stronger and oriented differently than many models had predicted. It revealed that the boundary is far more complex than a simple bubble edge. There are layers and transition zones where solar and interstellar particles mingle before the final crossing. Cosmic ray measurements provided new insights into how high-energy particles from distant stars travel through the galaxy, and the plasma density readings confirmed that the interstellar medium is far less empty than we once imagined. It is a dynamic, living environment shaped by the death of stars and the birth of new ones. Crossing the heliopause was not just a technical milestone, it was a philosophical one. For the first time, a human-made object had left the protective cocoon of our star and entered the wider galaxy. Everything Voyager 1 had experienced up to that point, Jupiter's raging storms, Saturn's glittering rings, the long years in the heliosheath had taken place within the Sun's sphere of influence. Now it was truly on its own, sailing through a realm where the Sun is just another distant point of light. The spacecraft had become an interstellar citizen, carrying with it the fingerprints of 1970s Earth technology and the collective curiosity of an entire species. What makes this moment even more extraordinary is the quiet drama of how it unfolded. There was no live television broadcast, no cheering crowds at mission control. The crossing was detected days or weeks later through careful analysis of faint radio signals. Yet in the quiet rooms at JPL, scientists felt the same sense of awe that explorers must have felt when they first rounded the Cape of Good Hope or set foot on the Antarctic ice. Voyager 1 had done what no other machine had ever done. It had pushed the frontier of human knowledge outward by billions of miles and opened a new chapter in our understanding of the cosmos. As we reflect on this historic leap, we realize that the invisible wall Voyager crossed is still there, still protecting our solar system from the harshest radiation of the galaxy. Every day, the heliopause shields Earth and all the planets from the full force of interstellar cosmic rays. Voyager 1's journey reminds us how fragile and precious that shield is, and how remarkable it is that a small, aging spacecraft could tell us so much about what lies beyond it. The data it continues to send back even now, years after the crossing, is teaching us that the space between the stars is not empty or dead. It is alive with particles, fields, and forces that connect every star in the Milky Way. The leap into interstellar space was not the end of Voyager 1's story. It was only the beginning of its true mission, the one it was ultimately built for. From that August day in 2012 onward, every signal it sends is a message from a realm we have never visited before, a realm that will one day be the destination of future human explorers. The silent journey had crossed its greatest threshold, and the whispers from the other side would continue to reach us, faint but clear, for years to come. In the vast, silent expanse where Voyager 1 now drifts, far beyond the last faint whispers of the sun's influence, there travels a message unlike any other ever sent by humankind. Encased within the spacecraft itself, protected by a thin aluminum sheath and etched in gold, is a time capsule that carries the collective heartbeat of our species across the interstellar gulf. This is the Voyager Golden Record, a 12-inch phonograph disc designed not for the engineers who built it, nor for the scientists who track its journey, but for any intelligent beings who might one day intercept Voyager 1 as it sails through the galaxy for billions of years to come. Launched in 1977 alongside its twin, this golden artifact is humanity's most optimistic and poetic gesture, a deliberate attempt to introduce ourselves to the cosmos, to say, in the most universal language possible, we were here. This is who we are. This is what we loved, what we feared, what we dreamed. The idea originated in the brilliant, imaginative mind of astronomer Carl Sagan and a small team of visionary collaborators who understood that Voyager's journey might outlast every living person on Earth. They had only months to decide what should represent an entire planet. The result was a masterpiece of curation under pressure, 115 carefully selected images encoded in analog form, 90 minutes of sounds that capture the living Earth, 27 musical selections spanning cultures and centuries, and spoken greetings in 55 languages. All of it was pressed onto a coppered disc coated in gold, mounted on the side of the spacecraft with a protective cover and an etched diagram showing exactly how to play it. The instructions are universal, drawn in scientific pictograms, a diagram of the record in stylus, a binary coded speed, and a pulsar map locating our sun among the stars. It is, quite literally, a message in a bottle cast into the ocean of space, with the faint hope that some distant shore might one day find it. Let us open that bottle together and listen to what it contains. The images begin with the most fundamental, a calibration circle, then a portrait of our solar system, followed by Earth from space, the continents, oceans, and the thin blue line of atmosphere that makes life possible. There are scenes of human life in all its diversity, a mother nursing her child, people eating, laughing, running, dancing, working in fields and factories, climbing mountains, sailing oceans. There are diagrams of DNA, the structure of a cell, the anatomy of a human body, mathematical equations and scientific instruments. Nature is represented in stunning detail. Snowflakes, trees, flowers, insects, birds in flight, a cheetah in mid-stride, a dolphin leaping, a sunset over the ocean. Cultural landmarks appear: the Taj Mahal, the Great Wall of China, an astronaut on the moon, the UN General Assembly. Everyday objects are included too: a page of sheet music, a supermarket, a highway at night, a radio telescope pointed toward the stars. Every image was chosen to tell a story without words, a visual encyclopedia of our world at the end of the 20th century. The sounds are even more intimate. You hear the wind rustling through grass, the crash of ocean waves, the crackle of a fire, the cry of a newborn baby, the laughter of children, the footsteps of a crowd, the heartbeat of a mother. There are the songs of whales, the calls of birds, the rumble of thunder, the patter of rain, the roar of a volcano, the buzz of an insect. Human endeavors are captured too: the sound of a tractor plowing a field, a blacksmith hammering iron, a train whistle, a rocket launch. These are not random noises, they form a sonic portrait of a living, breathing planet, rich with life and activity. Then come the musical selections, chosen to showcase the breadth of human creativity. Classical works by Bach, Beethoven, and Mozart sit alongside traditional music from Senegal, Peru, Australia, and Japan. There is a Navajo night chant, an Indian raga, a Georgian choral piece, and, famously, Chuck Berry's Johnny B. Good, chosen to represent the energy and joy of rock and roll. The inclusion of that track sparked playful debate at the time, but it perfectly captured the spirit of youthful exuberance that defines so much of human culture. The spoken greetings add the most personal touch. In 55 languages, from ancient Akkadian to modern Mandarin, people say simple, heartfelt phrases. Greetings from the children of planet Earth. We step out of our solar system into the universe. If you are out there, we wish you peace. Each voice carries the accent and cadence of its culture, a chorus of humanity united in curiosity. The final message, spoken by then UN Secretary-General Kurt Waldheim, expresses hope for friendship across the stars. These voices, recorded in 1977, now travel at the speed of light through regions where no human sound has ever reached. The physical design of the record itself is a triumph of symbolic engineering. The cover features a diagram of the record being played with a stylus, binary numbers indicating the playback speed of 16 Akuro revolutions per minute, and a map of 14 pulsars whose precise periods act as cosmic coordinates locating our sun. A silhouette of a human figure stands beside the diagram, providing scale. The instructions are deliberately scientific so that any civilization with basic astronomy and physics could decode them. Inside the protective cover is an ultra-pure sample of uranium-238, whose decay rate offers another time marker. The entire package was built to survive 1 billion years in the vacuum of space, resisting radiation, micrometeoroids, and extreme temperatures. What makes the Golden Record so profoundly moving is its optimism in the face of uncertainty. The team knew the odds of it ever being found were vanishingly small. Voyager 1 is heading toward the constellation Ophiuchus, and the nearest star system in that direction is more than 40,000 years away at the spacecraft's current speed. Even if another civilization does encounter it someday, they would need to recognize the disk, build a compatible player, and interpret symbols created by a species they have never met. Yet the act of sending it was an affirmation of hope. It says that we, as a species still young in cosmic terms, chose to reach out rather than remain silent. It says that even though we are tiny and our civilization fragile, we wanted the universe to know we existed, that we created beauty, that we loved, that we wondered. Today, as Voyager 1 sails through the interstellar medium more than 16 billion miles from home, the Golden Record travels with it, a silent passenger on an eternal voyage. The spacecraft's instruments continued their work, measuring cosmic rays and plasma waves, but the record itself needs no power. It simply rides along, a golden thread connecting 1977 Earth to whatever future awaits in the galaxy. In an era when our daily lives are filled with immediate concerns, the record reminds us of something larger, that curiosity and creativity are among humanity's greatest gifts. It challenges us to think beyond our lifetimes, beyond our solar system, beyond even our species. It asks us to imagine being the finders rather than the senders. What would we feel if we discovered a similar message from another world? The Golden Record is more than a collection of sounds and images. It is a mirror held up to humanity at a particular moment in time. It captures both our achievements and our imperfections, our science and our art, our wars and our peace, our solitude and our togetherness. It was created by people who understood that exploration is not only about discovering new worlds, but about revealing who we are in the process. As Voyager 1 continues its silent drift, the record travels with it, a quiet declaration that we once looked up at the stars and decided to speak across the emptiness. In the cold, dark reaches between the stars, this golden message keeps watch, waiting for the improbable moment when another intelligence might listen and understand. Its presence on board transforms the spacecraft from a mere scientific instrument into something far more profound, a vessel of memory, a bearer of culture, a testament to the human desire for connection. Every faint radio signal Voyager sends back to Earth is accompanied, in spirit, by this golden companion. Together they tell two parallel stories, one of data and discovery, the other of hope and humanity. And as we listen to the whispers still arriving after nearly 49 years, we are reminded that the most powerful messages are often the quietest ones, the ones sent not for immediate reply, but for the sake of being heard across the ages. The Golden Record is our legacy, etched in gold and carried on a current of gravity and inertia toward the unknown. It is a promise that even in the silence of interstellar space, the voice of Earth continues to travel, singing, speaking, and showing the universe what it means to be alive. In the chapters ahead, we will follow Voyager 1 deeper into its interstellar journey. But here, in this golden message, we pause to remember why the journey matters, because it carries not just instruments but the very soul of our species into the cosmos, a soul that, against all odds, chose to reach out and say hello. In the vast, silent expanse beyond the protective bubble of our sun, where the solar wind finally yields to the gentle currents of the galaxy, Voyager 1 continues its interstellar dialogue with Earth, a conversation that is now stretched across more than 16 billion miles and nearly 49 years. Today, the spacecraft operates in a realm no other human-made object has ever entered, sampling the raw interstellar medium and sending back data that arrives as the faintest of whispers after traveling for almost an entire day. These signals, transmitted with less power than a refrigerator light bulb, represent one of the most remarkable feats of long-distance communication ever attempted. Every bit of information that reaches our antennas is a triumph of resilience, a testament to instruments designed in the 1970s that continue to function in conditions of extreme cold, relentless radiation, and dwindling electrical power. The current interstellar mission of Voyager 1 is focused on three primary scientific instruments that remain active: the plasma wave subsystem, the cosmic ray subsystem, and the magnetometer. Together, they paint an ever clearer picture of what lies between the stars. The plasma wave subsystem listens for oscillations in the sparse plasma, the electrically charged particles that drift through interstellar space. In 2013, shortly after the historic crossing of the heliopause, this instrument detected a sudden shift. The density of plasma jumped dramatically, confirming that Voyager had indeed left the Sun's domain and entered true interstellar space. Since then, it has continued to record plasma waves triggered by solar outbursts that occasionally ripple outward like cosmic echoes. These waves travel through the interstellar medium at speeds far slower than light, allowing scientists to measure electron density and temperature in a region where particles are separated by centimeters rather than the dense clouds found inside our heliosphere. Complementing this is the cosmic ray subsystem, which measures high-energy particles originating from distant supernovae and other galactic events. Inside the heliosphere, the Sun's magnetic field deflects many of these particles, acting as a protective shield. Beyond the heliopause, Voyager 1 experiences a marked increase in galactic cosmic rays, energetic protons, electrons, and heavier nuclei streaming in from all directions. The data streaming back reveals subtle variations in intensity and direction that scientists use to map the local interstellar magnetic field and understand how our Sun's bubble interacts with the broader galaxy. These measurements are not just numbers. They offer a real-time glimpse into the high-energy environment that shapes star formation and influences the radiation levels future interstellar travelers might encounter. At the heart of this ongoing dialogue is the spacecraft's radio transmitter, a 23-watt system that has been broadcasting since 1977. The one-way light travel time now exceeds 22 hours, and by late 2026 it will reach a full 24 hours, one complete light day. When mission controllers at the Jet Propulsion Laboratory send a command, they must wait nearly 2 full days for confirmation that the spacecraft received and executed it. The returning science data arrives even weaker, often requiring hours of integration by the Deep Space Network's massive 70-meter dishes in California, Spain, and Australia. The signal strength at Earth is roughly 10 to the minus 16 watts, comparable to the energy of a single snowflake landing on pavement. Yet sophisticated error-correcting codes and massive receiving antennas allow engineers to extract meaningful information from this whisper. Each successful downlink is carefully scheduled, with the spacecraft's remaining power carefully rationed to keep the transmitter alive. Power management has become the defining challenge of Voyager's interstellar phase. The 3 radioisotope thermoelectric generators, once producing 470 watts combined, now deliver less than 230 watts total. Mission teams have executed a meticulous shutdown sequence over the years, turning off non-essential systems one by one to preserve energy for the science instruments. The cameras were powered down long ago after the planetary flybys. Many heaters have been switched off, allowing parts of the spacecraft to operate at temperatures far below their original design limits. The gyroscopes used for attitude control were turned off years ago, and the spacecraft now relies on a slow, steady spin to keep its high-gain antenna pointed toward Earth. Despite these constraints, the remaining instruments continue to operate with remarkable fidelity. The plasma wave subsystem and cosmic ray subsystem, along with the magnetometer, receive priority because they require minimal power and provide the most critical data about the interstellar environment. What makes this resilience so compelling is the age of the hardware. Many components were built with 1970s-era technology, magnetic core memory, discrete transistors, and analog circuits that were never intended to function for half a century in the harshest environment imaginable. Cosmic radiation has bombarded the electronics for decades, yet redundant systems and clever error correction routines have kept critical data flowing. Engineers compare the spacecraft to an elderly marathon runner who refuses to stop, conserving every ounce of energy while still delivering insights that reshape our understanding of space. Recent data from the cosmic ray subsystem, for instance, has shown unexpected variations in particle fluxes that suggest the local interstellar medium is more dynamic than previously thought, possibly influenced by nearby stellar activity or galactic magnetic structures. The dialogue between Voyager 1 and Earth is not merely technical, it is profoundly human. Teams of scientists and engineers, some of whom were not even born when the spacecraft launched, now pore over the incoming data with the same sense of wonder felt by the original mission designers. Each new batch of plasma wave readings or cosmic ray counts is analyzed in real time, published in scientific journals, and used to refine models of interstellar space. These faint signals have already revealed that the interstellar magnetic field is draped around the heliosphere in unexpected ways, that the boundary is more porous than predicted, and that high-energy particles from outside our solar system dominate the environment beyond the sun's reach. Every successful contact reaffirms that human curiosity can bridge distances that dwarf entire planetary orbits. Yet the conversation is slowly winding down. Power levels continue their inexorable decline, roughly 4 watts per year. Mission planners have already begun preparations for the eventual loss of instruments. The plasma wave subsystem may be the last to go, as it requires the least power. When the final transmitter can no longer sustain a usable signal, Voyager 1 will fall silent, becoming a silent artifact drifting among the stars. But until that day projected to arrive sometime in the mid-2030s, the spacecraft will keep talking, sending its precious data across the abyss so that we on Earth can keep listening. The ongoing interstellar mission of Voyager 1 stands as living proof that careful engineering and relentless human determination can extend a spacecraft's life far beyond its original design. Its instruments, though ancient by technological standards, continue to deliver groundbreaking science about a frontier we can only reach through such proxies. The faint radio whispers that arrive after nearly a full day's travel carry more than numbers. They carry the collective achievement of generations who built, launched, and nurtured this explorer. In the quiet darkness between stars, Voyager 1 keeps its promise to explore, to measure, and to report back for as long as its dwindling power allows. Each new data packet is a reminder that even in the interstellar void, humanity's reach persists, fragile, determined, and profoundly inspiring. As we listen to these distant voices from the abyss, we are reminded that science is not a sprint, but a marathon measured in decades and light years. Voyager 1's current dialogue with Earth is the culmination of everything that came before the launches, the planetary flybys, the boundary crossings, and the foundation for everything yet to come. The data it returns today will inform our understanding of interstellar space for generations, shaping future missions and deepening our appreciation for the vast ocean of stars through which we all drift. The whispers continue, faint but unwavering, carrying the story of a small machine that refuses to be forgotten in the cosmic dark. As Voyager 1 continues its silent drift through the interstellar ocean, we now stand on the threshold of a moment unlike any other in the history of human exploration. In November 2026, just months from the time these words are spoken, the spacecraft will reach a historic milestone that redefines what it means to be truly far from home. At that precise instant, the distance between Voyager 1 and Earth will stretch to one full light day, exactly 24 hours of travel time for a beam of light. When the probe transmits its next faint radio whisper, that signal will race across nearly 16 billion miles of empty space, arriving at our antennas not tomorrow, but the day after tomorrow. For the first time in history, a human-made object will be communicating with us from a distance where now and then are separated by an entire Earth day. This is the light day frontier, and its approach marks both an engineering triumph and a profound philosophical shift in how we understand our place in the cosmos. To truly grasp the magnitude of this milestone, let us pause and consider the numbers that make the human mind real. Right now, as you listen, Voyager 1 is already more than 16 billion miles away, roughly 165 times the distance from Earth to the Sun. Its radio signals, traveling at the unbreakable speed of light, already require more than 22 hours to reach us. By November 2026, that one-way journey will extend to a full 24 hours. Imagine picking up a phone and knowing that every word you speak will be heard by the person on the other end, only after a complete day has passed. That is the new reality Voyager faces. Every command we send, every instruction to adjust an instrument, to point the antenna, or to conserve power will take another full day to arrive. The spacecraft and Earth are no longer in anything resembling real-time conversation. We are now exchanging messages with yesterday and receiving answers from tomorrow. This vast separation brings with it extraordinary engineering challenges that the Voyager team confronts with quiet determination every single day. The spacecraft's transmitter operates on a mere 23 watts less power than a single dim refrigerator light bulb. Yet that whisper must cross billions of miles and still be detectable by our giant deep space network antennas in California, Spain, and Australia. To catch it, those 70-meter dishes must focus with pinpoint accuracy, collecting photons so sparse that the signal arrives with less energy than a single snowflake resting on the ground. Any misalignment of even a fraction of a degree, any unexpected power fluctuation aboard the aging probe, and the signal could vanish forever. Mission controllers must plan commands weeks in advance, anticipating every possible failure mode, because there is simply no time for rapid corrections. The round-trip communication delay will soon exceed 2 full days. In practical terms, this means the team is now operating a spacecraft that exists in a kind of temporal isolation, responding to yesterday's instructions while collecting today's data and preparing tomorrow's transmissions. Yet Voyager 1 continues to speak, and what it tells us about the interstellar medium is nothing short of revelatory. Beyond the protective bubble of the sun's heliosphere, the spacecraft is now immersed in the thin, cold plasma that fills the space between stars. Its plasma wave instrument still detects oscillations in this interstellar gas, revealing density waves and magnetic field fluctuations that originate from distant supernovae in the galactic magnetic field itself. Cosmic ray detectors register high-energy particles streaming in from all directions, particles that have traveled for millions of years across the galaxy before passing through Voyager's sensors. The magnetometer, one of the few instruments still fully operational, measures the subtle twisting of magnetic field lines that connect our solar system to the wider Milky Way. Each new data packet, however faint, adds another brushstroke to humanity's first real-time map of the interstellar environment. These measurements are not abstract numbers. They are the first direct samples of the medium through which our sun and every other star are drifting. In a very real sense, Voyager 1 has become a weather station for the galaxy. The approaching light day milestone also forces us to confront the limits of our technology and the beauty of its persistence. The spacecraft's radioisotope thermoelectric generators, once producing nearly 470 watts, now deliver barely enough power to run a handful of instruments and the transmitter. Engineers have already shut down heaters, cameras, and non-essential systems to keep the essential ones alive. Every watt is budgeted like a precious resource on a life raft. The onboard computers, programmed in the 1970s with less memory than a modern digital watch, continue to execute commands with flawless precision because they were built with triple redundancy and radiation-hardened components. The high-gain antenna, still pointed toward Earth with mechanical precision after 49 years of constant, gentle rotation, remains the only bridge across the abyss. This is engineering at its most poetic, machines that refuse to die, continuing their work long after the people who designed them have passed. What makes the light day frontier so compelling is the quiet drama it represents. Every successful signal received after November 2026 will be a small victory against the expanding gulf of time and distance. Scientists will wait an entire day for data that reveals the behavior of interstellar plasma, the strength of galactic cosmic rays, or the orientation of magnetic fields that stretch across thousands of light years. These readings are already reshaping our models of how stars and their protective bubbles interact with the galaxy at large. They hint at invisible structures, shock waves from ancient stellar explosions, and the gentle pressure of the interstellar wind that pushes against the edge of our solar system. In the coming years, as Voyager 1 drifts ever farther, these whispers will grow fainter still, yet each one will be more precious because it represents the outermost edge of human knowledge. Think for a moment about the human story embedded in this milestone. In 1977, when Voyager 1 left Earth, the idea of waiting a full day for a signal from a spacecraft seemed like science fiction. Today it is our lived reality with the farthest object we have ever built. The probe has outlived its original designers, outlasted multiple generations of mission teams, and now forces us to practice a new kind of patience, one measured not in minutes or hours, but in days and eventually weeks. It reminds us that exploration is not always about immediacy. Sometimes the greatest discoveries arrive slowly, carried across vast distances by machines that simply refuse to stop. As November 2026 draws nearer, the Voyager team is already preparing for the new rhythm of operations. Commands will be uploaded with even greater care. Data returns will be analyzed with fresh urgency because each packet now carries the weight of an entire day's journey through the cosmos. The milestone itself will pass without ceremony aboard the spacecraft. There will be no fireworks, no announcements from the probe itself, only the quiet continuation of its drift and the steady pulse of its radio beacon. Yet on Earth, scientists and dreamers alike will mark the occasion with a mixture of pride and wonder. For the first time, humanity will have an emissary that truly lives in tomorrow. This approaching light day threshold is more than a number on a chart. It is a symbolic boundary between the familiar realm where our signals could still feel almost immediate and the deeper interstellar future where communication becomes an act of faith and patience. Voyager 1 is teaching us that distance is not merely physical, it is temporal. The farther we reach, the more we must learn to wait, to listen, and to trust that the message will eventually arrive. In doing so, the spacecraft becomes a mirror for our own species, curious, resilient, and willing to send our questions into the dark, even when the answers take a day, a year, or a century to return. The light day frontier is not an ending. It is simply the next chapter in a journey that began with fire on a Florida launch pad and now continues in the silent dark between the stars. As Voyager 1 crosses this new threshold, it carries with it every hope, every question, and every piece of data it has gathered since 1977. And we, here on Earth, remain its faithful listeners waiting across the gulf of a full day for the next faint whisper that tells us what lies beyond the edge of our sun's domain. The milestone approaches, the signals continue, and the silent journey presses onward, one light day at a time, in the cold, unforgiving silence of interstellar space, where the sun is reduced to a faint pinprick of light and the nearest star still lies light years away. Voyager 1 continues its solitary voyage with a quiet determination that borders on the poetic. Nearly 5 decades after leaving Earth, the spacecraft's power reserves are dwindling, its instruments are being gently turned off one by one, and yet it presses onward, carrying the last embers of its original mission into a future that will stretch across thousands of years. This chapter of its story is not about dramatic discoveries or planetary flybys. It is about endurance in the dark, about the slow, graceful fading of a machine that refuses to be forgotten, and about the profound poetry of an object built by human hands that will outlive every person who ever touched it. The heart of Voyager 1's longevity has always been its radioisotope thermoelectric generators, or RTGs, 3 compact nuclear batteries fueled by plutonium-238. At launch in 1977, these generators produced roughly 470 watts of electrical power, enough to run a few household light bulbs. The plutonium decays naturally, releasing heat that is converted directly into electricity through solid-state thermocouples with no moving parts to wear out. This elegant design was never meant to last forever. Plutonium-238 has a half-life of 87.7 years, and the heat output drops by approximately 0.8% each year. By the mid-2020s, the three RTGs together generate only about 250 watts, barely enough to power a single microwave oven. Mission controllers at NASA's Jet Propulsion Laboratory now treat every watt like a precious resource, carefully budgeting power the way sailors ration fresh water on a long ocean crossing. To keep the spacecraft alive, engineers have implemented a meticulous power management plan that has unfolded over the past 2 decades. Non-essential systems were shut down long ago. The cameras were turned off after the Saturn encounter in 1980 because there was nothing left to photograph in the empty darkness. The ultraviolet spectrometer followed, then several plasma instruments that had completed their primary work. In recent years, the shutdowns have become more frequent and more poignant. The cosmic ray subsystem, the low-energy charged particle instrument, the magnetometer, and the plasma wave subsystem are among the last voices still speaking. Each time an instrument is powered down, it is done with surgical precision. Commands are uploaded across billions of miles. The spacecraft acknowledges receipt, and a small heater or transmitter is switched off to conserve energy. The process is never rushed. Controllers wait for confirmation that the data from the remaining instruments has been safely stored and transmitted before taking the next step. It is a dance of caution and care, performed across a radio link that now takes nearly 24 hours for a round trip. Even with these careful measures, the end of active science is approaching. Current projections show that by the early 2030s, only 1 or 2 instruments may remain operational. The plasma wave instrument, which listens for the subtle vibrations of interstellar plasma, is expected to be among the last to go silent. When the final walk can no longer support even that, Voyager 1 will enter a new phase, not death, but a quiet retirement. The spacecraft will continue to drift, its high-gain antenna still pointed toward Earth out of habit, though no more scientific data will be sent. The RTGs will keep producing a trickle of electricity for decades more, perhaps enough to keep the computer warm and the attitude control thrusters functional for orientation. But eventually, even those systems will fall silent. The plutonium will cool, the thermocouples will stop generating power, and Voyager 1 will become a silent artifact, coasting through the galaxy at 38,000 miles per hour on a trajectory that will carry it toward the constellation Ophiuchus. And yet, this is not an ending. It is a transformation into something timeless. After the last instrument falls quiet, Voyager 1 will continue its journey for tens of thousands of years. In roughly 40,000 years, it will pass within 1.6 light-years of the star Gliese 445, a red dwarf in the constellation Camelopardalis. In another 300,000 years, it may come within a few light-years of other stars. Over the course of 1,000,000 years, it will have traveled more than 500 trillion miles, still following the same gentle arc determined by the gravity assists of Jupiter and Saturn back in 1979 and 1980. The spacecraft itself is remarkably sturdy. Its aluminum structure, shielded against micrometeoroids, and its gold-plated components are designed to withstand the vacuum, the cosmic radiation, and the occasional dust grain for eons. Barring a catastrophic collision, which is statistically unlikely in the vast emptiness, Voyager 1 could remain intact for billions of years, a tiny metallic relic drifting among the stars long after the sun has swollen into a red giant and swallowed Earth. There is a quiet poetry in this eternal drift. Voyager 1 was never built to return home. It was launched with the understanding that it would become a permanent wanderer, a message in a bottle set adrift on an ocean of stars. Its silence in the distant future will not be failure. It will be the completion of its purpose. The data it has already sent back about the boundary of the sun's influence, the density of interstellar plasma, the flux of galactic cosmic rays will be studied by generations of scientists yet unborn. The golden record it carries will remain sealed, waiting for a finder who may not appear for 1,000,000 years. In that sense, Voyager 1 has already succeeded beyond any metric its creators could have imagined. It has become a symbol of human resilience, a machine that was given just enough power, just enough intelligence, and just enough hope to keep going long after its makers return to dust. As the power continues to ebb, the mission team on Earth treats each remaining month of data like a final conversation with an old friend. Commands are sent with extra care. Telemetry is analyzed with heightened attention. Small celebrations mark every successful transmission because each one is a victory against the second law of thermodynamics, against the natural tendency of all things to wind down. The engineers who monitor Voyager today were not even born when it launched. Many of their parents were children in 1977, yet they speak of the spacecraft with genuine affection, calling it our little spacecraft, or simply V1. They know that one day they will send the final command, and then the link will go quiet forever. When that day comes, it will not be with sadness alone, but with a deep sense of fulfillment. A creation that was meant to last 5 years has already endured nearly 50, and its journey will continue for thousands more. In the grand timeline of the cosmos, Voyager 1's active life is but the briefest flicker. Yet that flicker has illuminated more than we could have dreamed. It has shown us the shape of the sun's protective bubble, the gentle pressure of the interstellar wind, and the ceaseless rain of high-energy particles from distant supernovae. It has reminded us that exploration does not require constant drama or immediate rewards. Sometimes the greatest achievements unfold in silence, across decades, powered by nothing more than plutonium decay and human determination. As Voyager 1 drifts onward, growing fainter and quieter with each passing year, it carries with it the quiet poetry of endurance, the knowledge that something small, fragile, and beautifully engineered can outlast empires, outlast civilizations, and continue speaking long after its voice has grown too soft for us to hear. The dark is not empty. It is filled with the legacy of one small probe that refused to stop, even as its power faded and its instruments fell silent. Its eternal drift is not a tragedy. It is a triumph of foresight, of imagination, and of the human desire to reach beyond the horizon. And though the day will come when no more signals arrive, the story of Voyager 1 will echo through the ages, a reminder that we once built a machine that sailed into the night and kept sailing, long after we turned our eyes back toward the warmth of our own small world. In that long, silent future, Voyager 1 will not be alone. It will be accompanied by the invisible companions of human curiosity and wonder, drifting forever among the stars it was born to explore. As Voyager 1 continues its eternal drift through the interstellar darkness, we arrive at the quiet culmination of a story that began with fire and thunder on a Florida morning nearly half a century ago. This lone machine, now more than 16 billion miles from the blue marble we call home, has become far more than a scientific instrument. It is a living testament to human curiosity, a resilient whisper from our species that refuses to be silenced by the vastness of space. In this final reflection, we step back from the raw data and technical marvels to contemplate the deeper meaning of its journey, the legacy it carries, the wonder it awakens, and the profound way it reveals our brief yet luminous place within the cosmos. Consider for a moment what Voyager 1 truly represents. Launched in 1977 with technology that would seem quaint by today's standards, it has outlived its creators, survived radiation storms around Jupiter, navigated the intricate rings of Saturn, crossed the turbulent boundary where the sun's influence ends, and entered the interstellar medium as the first human-made object to do so. Its instruments, now powered by dwindling plutonium, still measure cosmic rays, plasma waves, and magnetic fields with a quiet determination that borders on the poetic. Every faint radio signal that reaches Earth after nearly a full day's travel is a victory against entropy, a reminder that something we built with our own hands continues to explore when we ourselves cannot. In an age when our attention spans are measured in seconds and our ambitions often focus on immediate returns, Voyager teaches us the power of long-term vision. It was never designed merely to visit planets. It was engineered to drift for thousands of years, perhaps millions, carrying the imprint of 20th century humanity into the galaxy long after our civilizations have changed beyond recognition. This silent journey invites us to ponder a future encounter that feels almost inevitable in its cosmic scale. One day, tens of thousands of years from now, or perhaps far longer, Voyager 1 may pass close enough to another star system for its golden record to be detected. That gold-plated phonograph disc, still attached to the spacecraft, holds 115 images of Earth. Sounds of wind and waves and laughter, music ranging from Bach's Brandenburg Concertos to Chuck Berry's Johnny B. Good, and greetings spoken in 55 languages. It includes instructions etched in symbolic diagrams, a universal language of science and mathematics designed to tell any intelligent finder how to play the record and where it came from. Imagine an alien civilization, perhaps orbiting a distant sun in the constellation Ophiuchus, toward which Voyager now heads. Discovering this artifact, they would encounter not weapons or declarations of dominance, but a humble portrait of our world. Children playing, oceans crashing, a single blade of grass, the UN building, a symphony orchestra, a mother nursing her child. They would hear our music, our laughter, our thunder, our bird song. In that moment, Voyager would become humanity's most enduring ambassador, a time capsule that speaks across epochs and species about who we were at the dawn of our spacefaring age: curious, creative, hopeful, flawed, yet reaching outward with open hands. The vastness Voyager reveals about our place in the universe is both humbling and exhilarating. From its current vantage point, the Sun is merely the brightest star in a sky filled with millions of others. Earth is invisible, lost in the glare. Our entire solar system appears as a tiny, insignificant speck. Yet this tiny probe, built by a species that has existed for only a cosmic blink, has already traveled farther than any other object we have created. It forces us to confront the reality that we are not at the center of anything. We are passengers on a small rocky world orbiting an average star in a spiral arm of an ordinary galaxy, and still we dared to send a message into that immensity. This paradox, our cosmic smallness paired with our boundless curiosity, is what makes Voyager's story so profoundly moving. It shows that even in the face of infinite emptiness, humanity chooses connection. We choose to explore, to learn, to leave echoes of ourselves among the stars. As we listen to the faint signals still arriving from the abyss, we are reminded of the resilience embedded in the spacecraft's design. Its radioisotope thermoelectric generators have lost more than half their original power. Yet mission controllers carefully ration every watt, shutting down non-essential heaters and instruments one by one to keep the transmitter alive. The spacecraft itself will continue its journey for hundreds of thousands of years, perhaps even millions, before its orbit brings it anywhere near another star. During that time, it will encounter the gentle interstellar wind, pass through clouds of dust and gas left by ancient supernovae, and eventually become a silent relic drifting through the galaxy. Future generations of scientists, or perhaps civilizations we cannot yet imagine, may one day retrieve it and marvel at the fragile technology that carried our voices across the void. In that distant future, Voyager will no longer be just NASA's probe. It will belong to the cosmos itself, a relic that tells the story of a young species that once looked up at the night sky and decided to answer its call. This legacy extends far beyond engineering or data collection. Voyager 1 inspires us to think differently about time, about distance, and about what it means to create something that outlives us. In a world that often feels rushed and fragmented, it stands as a monument to patience and perseverance. It reminds us that the greatest achievements are not always the loudest or the most immediate. Sometimes they are the quiet ones, the patient signals sent across decades, the steady drift through darkness, the unwavering commitment to knowledge, even when the payoff lies centuries ahead. It also speaks to our shared humanity. The scientists, engineers, artists, and dreamers who built and launched Voyager in 1977 could not have known that we would still be listening in 2026, still marveling at its resilience, still using its data to refine our understanding of the interstellar medium. Their work has become a bridge across generations, connecting us not only to the stars but to one another. As this silent journey draws toward its reflective close, we are left with a sense of profound humility and quiet hope. Voyager 1 reveals the universe's staggering scale, while simultaneously affirming our small yet meaningful place within it. We are creatures of a single planet who have already reached beyond our solar system. We are storytellers who have sent music and laughter and images of our world into the galaxy. We are dreamers who built a machine that continues to speak long after its builders have gone. This is the enduring power of the interstellar drift. It transforms a simple spacecraft into a symbol of what humanity can achieve when we look beyond ourselves. It invites us to carry that same spirit of curiosity and resilience into our own lives, to ask questions, to explore the unknown, to leave something beautiful and true behind for those who come after us. In the end, Voyager 1 does not belong only to NASA or to the United States or even to the 20th century. It belongs to all of us, to every person who has ever gazed at the stars and wondered. Its silent journey continues year after year, carrying our collective wonder into the dark. And as we return our attention to the quiet beauty of our own night sky, perhaps we can feel a little closer to that distant traveler. We are not alone in our curiosity. We never have been. The echoes among the stars are our own, and they will keep traveling long after we ourselves have become part of the cosmic story. Thank you for joining this journey through the silent odyssey of Voyager 1. May its story linger with you, a gentle reminder that even the smallest voice, sent with care into the infinite, can echo forever. The cosmos awaits, and we, with open hearts and curious minds, continue to reach.